Okay, with that said, we can get started. So there was a question before we get started. There was a question about deep learning with PyTorch, a Udacity course that could be helpful as an aside or as an extension of your recitations. But to be clear, part of the recitations will be built along the lines of this Udacity course. So it's not like the course is necessary for you to take part in the recitations, but it might be helpful to look at it in addition to the course. Cool. So today we are talking, and let me share my screen as I say this. Today we're talking about maximum likelihood and maximum posteriori, but I want to start with this question of when I moved to the US as a graduate student. One of the first things my family asked me was, "Have you started eating pizza?" And I was like, I was very afraid of getting addicted to pizza because that's a thing. You get pizza for $1 and then suddenly you can't stop. But I still tried a couple of slices, and we went to a bunch of places, and then the question that came out of it also. If you have a burning question, please raise your hands and the TAs will notice you. I do have the chat open just in case. But anyway, let's go back to what I was saying. So what I was saying is the question emerges, what's the best pizza in New York City, right? And for me, I'm not a huge fan of lots of toppings on pizza. And so I decided that, hey, for me, um, the best pizza in New York is this slice on the bottom left, which is called the mozzarella basil pie. It just has like sauce. It has a bunch of mozzarella. It seems like it has some garlic, and it has a bunch of basil leaves sprinkled on top. And I'm happy with this pizza. So for me, maybe this is the mozzarella basil pie. But what happened was when my friends got me this set of pizzas, they didn't tell me where they got them from. They just gave me a couple of slices because they were like, "We don't want you to go on the internet, look up what is the best pizza, and then tell us that. We really want your opinion. Like, what is the best pizza?" And so once I selected this best pizza, the natural next question was like, well, where can I get more of this pizza? Which is, what is the pizzeria that could have made this pizza? And there were a couple of options because I knew my friends had gone to one of these places, or at least it was reasonable to believe that. And so, sorry. And so I was like, okay, pizza was made by one of these places. The next thing I can do is think about what are the pizzas like at these different places, and I want to figure out this top right corner, what pizzeria could have made this slice. So I'll pause here for educated guesses on based on the pizza that you see coming from these places. And these places are Domino's, Pizza Hut, Joe's Pizza, and Mario's Pizza. Um, Are there any guesses on which pizza place could have made this mozzarella basil pie? Joe's Pizza for sure. We have one of them. More guesses? Mario's Pizza, Joe's Pizza, Joe's Pizza. Okay, I'll pause here and wait for like someone to unmute and tell me why they feel like it's Joe's Pizza. You can raise your hand, or you can go ahead. None of these is another option. This pizza might have been made elsewhere. Um, I didn't say that, but sure. Um, I I'm very curious. Domino's and Pizza Hut are offensive. Okay, great. That's one of the options. Any other explanations for why this couldn't have been made at Domino's or Pizza Hut? And again, I'm not saying that's the right answer. I'm just asking you because everyone who posted said Joe's or Mario's. Is there some reason no one is posting about Domino's and Pizza Hut other than the fact that they might be offensive? to some people. Like I said, you can unmute yourself. We can discuss this through because this is important. This is a fundamental running example that we will use to explain some very core mathematical concepts for machine learning. Okay, so Salva has one explanation. He says Domino's put a lot of toppings and olives and stuff. I feel like this is fair. Anyone else? No brave soul willing to unmute and engage in a conversation?
From the picture,
Maybe
we can see like the
tomato
juice
sauce
people.
proportion.
I don't know if this is Priyambi, Hiran, and Arvind.
Yeah.
Okay, so Priyambi, can you go first?
So basically, from the picture, like under Joe's pizza, we can see like pizzas are mostly cheese topping, like cheese and toppings are not there. So and you can even see a similar piece in that. So maybe one of the
Very interesting. Okay, Arvind.
Maybe the tomato sauce proportions are very similar. It looks like this also has a lot of tomato sauce compared to other.
Fair enough. So both of these get at the fact that these samples of pizza from Joe's, and by the way, these are both fantastic explanations. So thanks for engaging. Oh, and the message as well. Maybe Joe's because this pizza is way too ugly to be part of a big restaurant chain like Domino's and Pizza Hut. Okay, so we have people throwing shade at multiple pizza chains out here. Great. But yeah, in general, you are right. The explanation for this, at least the one I would buy, is that look, the slices from Joe's look the most similar to this pizza that is the sample that we want to match. And it just seems not plausible that the other pizza places would produce this pizza. And I mean, I would buy that. Like this slice, for example, circled in black, and one of these slices from the data that we have, which is the MBP or the mozzarella basil pie that I really liked. They seem pretty similar. So I would buy your explanation if you said Joe's Pizza probably produced this. But what you have essentially done, in a sense, is you've looked at the different pizzas produced by Joe's. You've looked at which pizza is most likely to produce the data at hand, which is the best pizza that we want to recover. And you internally gone through this procedure of saying, well, this pizza is similar, the other pizzas are not, so the other pizza places could not have produced this final pizza. And it is, in a very hand wavy sense, you've done maximum likelihood estimation. But what is this maximum likelihood estimation? Well, we've discussed models, parameters, data before, so I'm not going to define them. But in this context, if you think about the model as your pizza chain, and going back to pizza chains, we have these four models. You have different sets of parameters. And if I call parameters as ingredients for pizza making, then these types of different pizzas, so the mozzarella pizza, the margherita pizza, the veggie pizza, the pepperoni pizza, all of these are different settings of some parameters that is producing this data. That the data is the pizzas, right? And then the maximum likelihood estimation question is, what's the recipe for the closest pizza to the mozzarella basil pie that can be made at this pizza chain? So what you're saying is, if the closest pizza at this chain is the most similar to the data that I've observed, then I will go with guessing this as my best model. So that, in a sense, adds a step of selecting the model and then going for the parameter estimate, but we'll get to that. So yeah, so essentially you've done maximum likelihood estimation for a bunch of different models and selected the one that's given you the closest estimate. Typically you select one model, and then you go ahead with that, but you can also consider an additional step of selecting the correct model. So let's pause here and go through each of these things. So there is a pizza chain, which is your model. There are parameters, which are your ingredients for pizza making. There is data, which you want to maximize under this model. So this the mozzarella basil pie that you want to consider as being produced by this pizza place, and then see how close you can come to this ideal mozzarella basil pie that I want. And so that's the question for maximum likelihood estimation. And you get a certain point estimate out, which is what, like if I go to Joe's Pizza and I ask him for that mozzarella basil pie, then he'll tell me some approach to make this pizza. So it has 300 grams of dough, it has 90 grams of mozzarella, it has 2 tablespoons of sauce, a couple of leaves of basil, and then salt. And I missed out garlic, but probably also garlic. And so he gives me this fixed pizza, this fixed set of ingredients in this entire space. Remember that the parameter space implies there are different kinds of pizzas. There are veggie pizzas, olive pizzas, margaritas, also a mozzarella pizza. So that's what we're going for. So we search through this parameter space for the fixed point, which is the best pizza, and that we are saying is maximizing our likelihood of Joe's Pizza producing the mozzarella basil pie. And all of this seemed to be like your brain did in seconds, and you didn't even realize what you were doing until like you came up with the answer, and I told you this is probably what your brain is doing. Which is why it's super cool that someone mathematically formalized these things, wrote them down as theorems, and we apply them in machine learning every single day. So to describe the process in great detail, you in your head, you picked a pizza place to work with. You said, okay, let's say I start with Domino's. Okay. And I think about the kinds of pizzas that Domino's makes. I add a couple of ingredients to pizza. If it tastes more like the mozzarella basil pie, that's great. If it doesn't, then stop adding that ingredient, add new ingredients. Repeat this for different ingredients and stop when pizza no longer continues to taste similar to this mozzarella basil pie. And in your head, you estimated that given the data produced from this Domino's stuff, it's really not similar to the mozzarella basil pie. So it probably won't taste as similar to this as a pizza at Joe's would taste. So given Joe's, all of you thought about this process of how you could get close to this ideal pizza. You thought about which slices work, which slices don't work, which ingredients work, which ingredients don't work. And then you got to a point where you said, okay, at Joe's, this is very likely to be the case where I might produce the correct mozzarella basil pie or something extremely close to it. So what you just did in your head is sort of like gradient descent, because you probably thought about how it would taste if you added some ingredients and you're like, this doesn't have olives, so adding olives might not make sense. This ideal slice does not have broccoli, so adding broccoli might not make sense. It doesn't have pepperoni, so adding pepperoni might not make sense. Um, um, and if you think about that a little differently, and if you were actually tasting these slices and figuring that out, then that would be sort of gradient descent, because you're testing, stopping when it doesn't taste similar. In a gradient descent, you're going downwards, stopping when it no longer tells you that the slope is this direction. If it tells you the slope is the other direction, you go in the other direction. So again, very hand wavy explanation, but hopefully it conveys the point of how these things do apply in real life, and often when we don't even think about them. And then there is another approach where someone might argue that, okay, sure, this looks similar, but for them, this other slice also looks similar. Like they don't care about the basil flavor, but they just want the sauce ratio. As someone pointed out, it has very less cheese and a lot of sauce. So then in that case, according to their loss function, there is a different way to optimize this. And so you might think of placing a set of probabilities like, okay, I think this might work. This has a 50% chance of being similar, but I think this also has a 30 or 40% chance of being similar to the output. And that's where I start. That's the ingredients that I start with. And those are the priors that I place on my data. priors are by definition your prior beliefs before you see any of the data. So if I had to ask you, yeah, in this case, maybe it's not a great idea to start with priors, but in general, okay, well, if I had to place a prior, I would probably say I think a margarita pizza might be a good start generally to get to a mozzarella basil pie, because I know before looking at anything that margarita has tomato sauce and cheese. Mozzarella basil pie at least has tomato sauce and cheese. So that's my prior belief. It may or may not be wrong. Priors can be very wrong, but the idea is priors will be updated. So in this ingredient space, even if you start in a very small corner, you will eventually get to the space of get to the point where it is the correct set of pizzas that you want to align yourself to. So in maximum likelihood, you get point estimates. You get 1 point. That is the answer. In maximum a posteriori, you get a distribution. So you might end up with something like, okay, if you look at the last line here, and I lost my cursor. Wonderful. Okay, if you look at the last line without following my cursor, I'm talking about the posterior. It now tells you a distribution like between 250 and 300 grams of dough, between 80 and 100 grams of mozzarella, between 2 and 4 tablespoons of sauce, between 5 and 8 leaves of basil, and between 2 and 6 grams of salt. So it doesn't tell you exactly the point, but it tells you roughly between these values is where you will end up. Which is in a way also better, because when you're making pizza, you have a little more confidence that, okay, as long as you're within 250 to 300 gram, you're good. Whereas in the other case, you don't know if, and remember this, it says 300-gram dough. So does it mean 290 might be okay, or does it mean 310 might be okay? Like which side is better to fall on? Because if I can't measure it out perfectly, then I don't know how good or bad my estimate is, right? So it's slightly easier to work with in the pizza example, a distribution. Oh, my cursor reappeared. Nice. Distribution over these things as opposed to a point estimate. And again, in different cases in life, so at some points you might really care about how uncertain you are, in the sense, is 300 grams better, is 310 grams better, or 290 grams better? In some cases you might really want to know that. In other cases you might not care. So depending on that, and depending on your choice of if you actually have good priors to start off with, like if you are a chef, you will have good priors. You will know how a certain pizza was produced. So Fennel raised an important point that a map can still give you point estimates. So if you consider between 250 and 300 grams, exactly in the middle, that's 275 grams. That's still a point estimate. But in general, like a prior is updated into a posterior. So correct me if I'm wrong. I think I clarified. You can unmute yourself if you like.
No,
So
it's right.
yeah. So even though you have this final distribution, you can still end up with a point estimate just by taking the mean. So between 250 and 300, sure, I'll take 275. Between 80 and 100, sure, I'll take 90. So in the map estimate, it's not that you will always have a range only. You can still derive a point estimate from this range. But it's nice to have this range because now you know which side you want to fall on. Cool. So I'll pause here before moving on to the math and like describing all of this in formal terms for any questions you might have. Okay, if there are none, hopefully you followed this example in these two cases, maximizing the likelihood and maximizing the posterior. And I feel like, yeah, most of you are already, we had Bayes theorem in the homework, in the application form. So I assume you at least know about some parts of Bayes theorem where your prior is updated into your posterior using the data that you have. And I've already walked you through this, correct me if I'm wrong, but so I'm not going to spend time on that. I will get directly into the math. So let's go back and talk about this normal distribution, this Gaussian distribution, this bell curve that we've mentioned so many times. You said that, set of independent random samples. Oh, sorry. Before that, I have a question in the chat. For a posteriori estimation, we're dealing with labels of ranges, right? Could you clarify what you mean by labels of ranges?
Yeah, so my question was that like we are estimating the ranges of the what do you say the ingredients. So we would require like data set that gives that provides us with ranges, or should it just lie with like normal like labeled, I mean sorry, point numbers?
So that's a great question, and maybe I can illustrate it with a diagram about what I mean when I say, like, the answer to this is that you can still use point estimates to update your ranges. Let's go back to this. So what I said originally was that if you have a certain distribution and you have a certain point, how do you update this distribution to account for this point, right? Can someone guess? I don't know if it's easy to explain on.
Maybe move the mean further, right?
I think that's fair. So something like that, right? Except passing through this. Sorry about that, but something like this, right? Do you buy this? If you're saying something, you're on. Yeah, okay. Okay,
Yeah, yeah, I agree.
Yeah, so in the same way that we would optimize using data points before, now we're just updating our distribution to account for these ranges. So we're updating our ranges to account for these different points. So something like this, or maybe something like this. And so you started with a range without knowing where it fell, which was this one. And then at each data point, you started updating this function or this range to account for the new data that you saw. And at some point, you might even ignore this and draw something like this. So you still have a range of values and the probabilities for each values. But now you're updating it just based on single data points. It's not a range, right? This is still a single point. Is this fair?
Yeah. So like we are only dealing with the mean and standard deviation of the range we want to find, rather than
Yes.
regressing it along like curve fit.
Yeah, you're essentially fitting this curve. If you say this is a normal distribution, then you're moving this normal distribution to account for the new data points. So in a sense, you're updating your mu and sigma to mu dash and sigma dash.
All right, thank you, thank you. That was a great example.
Sure. And going back to the cool. So remember the distribution that we talked about, and let's say that my data follows this distribution. So now I have a certain data set which adheres to this distribution. So the functional form for the normal distribution is, oh man, really hate losing my cursor. I wonder, is it safe to assume a normal distribution every time? Well, safe, I wouldn't say. Generally it's safe to assume any distribution because it is an assumption you're making, and by definition assumptions are not safe. But among the set of assumptions people make, they commonly assume normal distributions because of this idea that any set of independent random samples is going to follow a normal distribution. So in that sense, yes, it is safe to assume a normal distribution, but I don't know why I keep losing my cursor. Side only. Let's see. Maybe this is better. Okay. Hopefully this works better. And I assume you can see my screen. So yeah, that's my answer to is it safe? Well, no, but if you have an assumption to make and you don't have a better idea, then yeah, sure. If it works, then you should assume that this is normally distributed. Joseph mentions in stats, assuming a distribution is like mapping out a physics equation. You have to understand which works in one context or another. I think that's a fair analogy. Yeah, it has to do with the problem specific understanding you have, and that again brings me back to this idea of priors, where you have some information. You know that if you touch a hot object you will burn your hand, so you want to assume that your hand is as far away from the hot object as physically safe. So these are like, again, like your prior is based on past experience, not on the data that you have seen. So it's good to get experience. Okay. Back to our point. So flashback to the normal distribution. Remember that we had a mean and a certain variance for the normal distribution, and we had estimates for the mean and the variance. So sample mean was defined as 1 by n, the sum of all your sample data, right? So sum of data by number of data points. That's all this is saying. The sample variance was defined as 1 by n, the data minus sample mean whole squared for each individual point. So if any of this is unclear, I would refer you back to the previous lectures and probably the recitations. But the question is like, why are the sample mean and variance defined this way? So going back to the first principles and like figuring it out how people define these things, and what Smola does is really nice because this is useful for a lot of machine learning, where you have to estimate these parameters for arbitrary distributions. Well, okay, so let's start with the data likelihood, and all of this estimation of sample mean and sample variance goes back to the likelihood of the data and maximizing this likelihood. So if you have a certain data set drawn from a normal distribution, why do we define the sample mean as sum of all samples upon number of samples, and why do we define the sample variance as sample minus mean whole squared by n for each data point? And so it all goes back to maximizing the likelihood of the data under this normal distribution. So it's like saying if my pizza place is this normal distribution, like this is the kind of pizzas it produces, then this is the best sort of description of this pizza that I want to obtain. This is the closest way to come to produce this MBP, mozzarella basil pie. That was the data, the pizza I liked. So again, this is exactly what it says, except in math. So this says probability of x parameterized by some mean and some sigma squared is now equal to, and remember that this is the IID assumption, right? So, and I need to switch between these two things, which isn't ideal, but maybe you can see my annotations. Nope. Yes, you can. Just checking that people can see my annotations. I just erased it, but I assume you can see it. Please post in chat if you can. Okay, cool. Then I'm going to start writing like this. So this is the model for the data. We said that the model for the data fits this distribution, which is parameterized by this mean and this variance, which is a normal distribution. Parameters. Cool. Parameters for normal distribution, right? And we are saying that by the IID assumption. What was the IID assumption? Does someone remember this? The full form for this? Independent and identically distributed. Thank you. I got a message. You assume your data points don't influence each other in any way. True. It's the same as saying two coin flips are independent. So one coin flip does not affect the next coin flip, vice versa. So it's just saying these are all independent samples that are drawn from the same distribution, so identically distributed. Oops. Independent and identically distributed. Yep. So as Joseph says, this is exactly what we're writing down. The joint distribution of x1, x2, ... xn is equal to the product of each of these. Oops. Product of each of these independently. So that's what this assumption is saying, and this is the same thing that is written here. So if capital X is equal to, okay, it's written here already. If capital X is equal to all of these independent data points, then the probability of this data, or the likelihood of this data, is equal to a product of the likelihoods of these individual data points under this model. What do I mean by under this model? And now I'm working within a pizzeria, and I'm saying that within this pizzeria, this is how I am going to, this is how probable these individual data points are. So under Joe's pizzeria, the data points are probably more likely. Under Pizza Hut, these data points are less likely. So what I want to do is I want to find the best possible likelihood. I want to maximize the likelihood, which is saying what? Like if I'm at Pizza Hut, which is the best, and best in the sense closest to this mozzarella basil pie that I'm going to get. So right now our model is the normal distribution. So we're saying under the normal distribution, what is the best mu and sigma that can describe the data that I have. So this is the data that I have. This is the mozzarella basil pie. And I want to maximize. Oh wow, I've been drawing with my fingers. So that's what this maximization is doing. Maximize the likelihood that data was generated by model, or equivalently pizza was created at pizza place. So the practical way of going about this is, again, like we've discussed, we want nice functions that we can work with in a gradient-based setting. So instead of maximizing this, we minimize its negative counterpart. So plus 5 is equal to minus of minus 5, right? That's a very bad start to this explanation. I feel like this is fair enough. Like maximizing one term is equal to minimizing its negative log. And why does this log taking work? Well, log is a one-to-one function, right? So it will map a certain function to something like this. This is log x. And what we're saying is minus log x is then something like this. No, something like this. Y minus log x. What am I doing? I'm spazzing out. If I take the negative of this, then it just flips, right? Flips at the x-axis like this. Cool. It minimizes at a certain point. I think that's what I'm doing. I guess someone can correct me if I'm missing something. Okay. In any case, maximizing a term is minimizing its negative counterpart as long as it's a one-to-one mapping, as long as this function doesn't mess something up, like map it to multiple values or something like that. So yeah, as long as it's one-to-one, the minima will still correspond to the minima of a function. And that's all I should say about that. So how are we on time? About 30 minutes in? No, 40. Yeah, about an hour in. Okay. Cool. The way we do this, actually, I should ask you, can someone tell me how you minimize or maximize a function with respect to some parameters? This should be calculus. I like it. Slightly more specific answers. I mean, I know you know the answer, but like
You differentiate it twice and then see greater than 0, less than 0, and minimum, maximum.
so the differentiating twice is to see whether it's maxima or minima. That is perfectly technically correct. The differentiating once is to find the maxima or minima. Thank you for that answer. Equate the derivative to 0, exactly. And that's exactly what we're doing, except now we're working with two multivariable calculus. So we're working with partial derivatives as opposed to derivatives. By which I mean mu and sigma square are both parameters of this, right? Yeah, so I think you have covered this in one of the classes, that the reason we choose logs are because we have very tiny numbers that we work with. Sorry, we want to work with manageable numbers as opposed to very high and very low numbers. And the log just allows us to do that. If it's very small, it will give you a negative number. If it's very high, it will give you a slightly positive number, but it will give you like a much lesser number than the magnitude of what you would otherwise be working with. So that's why we use log derivatives as opposed to just taking the just maximizing or minimizing the original equation on the left. Thanks. Okay, I've spoken a lot about this. If there are questions, you can interrupt me. Yes, using products results in overflow or underflow. These are excellent and very valid points. So that's why we use logs. Another super important point. Okay, you already know this more than I do. The log also converts it into a sum instead of product. So as we can see, now minus log. Okay, I should annotate what I'm talking about. Now minus log px is converted to a sum instead of a product. And this is just a decomposition of what we originally said px was. So this px is this equation. If you take minus log of this, you get a separate term out for this part, a separate term out for this part, a separate term out for this part. Okay, clearing that out. Let's go back to the slide we were talking about. Yep, so we decompose the likelihood into a certain sigma square related part, a certain exponent related part, and we are saying now we want to, what are we saying? Yeah, just summing this. This is a, oops, I think this is fairly straightforward. Like you're just expanding this out, like sum this term and then this term remains as is. Well, you're separating out the sums for each of them. And I don't want to say more about that, except for the fact that now this term is minimized at the value of mu is equal to 1 by n times summation summation. So this allows you to find the sample mean, because the sample mean is the quantity that minimizes this term, and minimizing that was maximizing the likelihood. So the data is most likely under the model if the sample mean is set to the sum of points upon the number of points. Is this motivation enough for people to understand why the sample mean emerges? Like why the sample mean is an estimate, right? It's not necessarily the true mean. So if you see like 5 pizzas and they are good pizzas, then you say that I think this is a good pizza place. That does not mean you've seen all the pizzas from that place. That just means you're taking a sample mean and saying that I think this is a good pizza place because it produced 5 good pizzas. On the other hand, if you have 2 bad food items or 5 bad food items, you're going to say it's a bad place because I've had bad food items there. It does not mean you've tried every single food item. So you don't know the true average of food items. You just know the sample average, and you're taking that to mean that the restaurant is not great. So like I said, you apply these things in real life far more often than you realize. And when we see math on paper, it definitely does not translate to, oh, I thought that food place was bad because I sampled a couple of items and I thought these items were bad. It's exactly the same, but you don't think about it. So hopefully that's clear. I will pause for a minute before moving on to the sample variance. By pause, I meant pause for questions if there are any. You could just as well arrive at this by taking the gradient with respect to the mean. Okay, so in a sense, if there's a question in the chat, so in a sense, if the data is bad, then there could be a better estimate than the sample mean. Data is bad. I use the food example to say that the taste of the food was bad. It does not mean that the data is bad. Sorry. I think I get what you mean. If the data is poorly representative of the true data generating process. So if I go to a restaurant and I happen to order the worst possible items on its menu, just by chance, whereas it's actually a really good restaurant, but I just chose really bad items. Yes, that's an unlucky case where your sample mean would be a bad estimate of the restaurant quality. So yes, that does happen, but on average, on average, like if you go to that restaurant 5 or 10 times and you try you try some random set of items, you're going to realize that it's a good restaurant. So that's again in expectation. That's what mathematicians would say. And what does in expectation mean? In expectation just means you go to the restaurant a couple of times, not just once, couple of items, and that's it. Right? In expectation, you would assume, you would expect that restaurant to be good. Okay, keep harping on the same point, but okay, cool. So moving on to variance. Thank you for that question. That was an excellent question. That was very, very relevant. Like sometimes you can just get unlucky. And there is nothing you can do about it. It's just bad. But if you keep, that's also motivating this idea of why people repeat the same machine learning process with different random seeds. That is just because you might just have gotten lucky with some random seed and everything magically worked out. But your method is not really good. So that's why they say that test this out with different random seeds and then tell us the average of the results. So it's again the same point. In expectation, is your method performing well or not? Cool. Estimating the variance, pretty much the same thing. Take the likelihood, differentiate with respect to the variance, set the gradient to 0. What do you get? Well, you get your you get this, which is your sample variance. And there is a different discussion to be had about, is this an unbiased estimate of the true variance? And it is not. What I mean by unbiased? Well, you said that sample mean on average converges to true mean. If you try different dishes out at the same restaurant many different times, on average or in expectation, you're going to converge to the true mean, which is to guess if the restaurant quality is actually great or not. But with variance, that's not the case. You have a certain bias or offset, unless you use this, replace this with 1 n minus 1, if I'm not mistaken. But that's, again, like I said, a different discussion to be had. For now, we'll just figure out that this is how you find the sample mean, find the sample variance. And so maximum likelihood estimation says, if you set if you set these parameters to the sample mean and sample variance, then this is the maxima, this is where you will arrive at. Remember that this maxima, keep drawing like this. Remember that this maxima is the negative of the minima that you found, conversely. So negative of the log minima that you found. But anyway, so that is in essence the mathematical version of maximum likelihood estimation. Okay, there's a question in chat. No, comment in chat. In math equations, expectation of the approximate mean, or to be clear, to be more precise, estimated mean is equal to true mean. Yes, but expectation of approximate variance is not is less than the true sigma. Yes, this is true. I should say sigma squared because it's expectation of variance, not standard deviation. But yeah. This is helpful. Cool. So I'll again pause for 30 seconds for 1 or 2 questions if there are any. Also, you can feel free to unmute if you want to. Okay. If not, then here are a few examples of where your maximum likelihood estimate might get you. And this is where or how you could end up with certain solutions. I should drop this off. Avoid confusions. So yeah, your maximum likelihood estimate basically finds the peak of your density and says, here, this is the maximum of your likelihood. But sometimes you want to know a little more, right? Like this peak versus if I had a certain distribution that was still peaked, but now it had something here. Like Maximum likelihood would not tell you the difference between this red one and this blue one, right? It would still say like here. And sometimes, like I said, you want to know more than just this much. Like sometimes you want to know what other pizzas might be close. Not the closest, but at least like reasonably close. For people who suppose like mozzarella basil pie, but they don't want that much mozzarella. So what other slices can you order? Someone might not like basil, in which case you go back to the example where you only had tomato sauce and mozzarella. And then you want like, okay, what is the closest I can come? And so I'm sort of getting at the point that you want a distribution over things and not just a fixed point. Like you want to know if I reduce my the amount of dough in this, will it still be okay? If you not perfect, but like still okay. And so having a distribution would really help as opposed to this point estimate, right? So someone telling me something like, okay, here it falls, but here, oh, sorry, I should not do that. Here it falls steeply, but here it doesn't fall as steeply. So maybe another point that I could go for is this, or third point I could go for is here. Like that's when I have a certain distribution, and that's the a posteriori estimate. So you have a range of values. That's again, we already discussed this, but that's what I'm getting at. And the example Alex Mola uses is very nice. So I'm going to use replicate his explanation. Suppose you didn't do your reading for last week, right? And your explanation for doing this was my dog ate my reading, or call it homework. My dog ate my homework. I was abducted by aliens. I was too lazy, and I had a sick grandmother. Um, it's not a great time to use sick grandmother as an example because most of us have seen some really tough times. So I'm not going to rely on that one, but I'm going to at least use the other three as examples. Um, dog ate my homework is an explanation. How plausible? We'll discuss it in a bit. Abducted by aliens is again an explanation, and we can again argue about how plausible this is. Where right now we're discussing what possible explanations could exist for the data being the student didn't do the homework. So you can also go back to the pizza example and use the same sort of which pie is closest, mozzarella, this, that, whatever. So yeah, I'm relying on his example for now just to have a sort of change of setting. And sure, all of these are plausible explanations for the data, but we don't know which is the most plausible. So I should clear this out. So then the question arises, should we believe all of these examples? Like if you go to the TAs and you say that, oh, last week I was abducted by aliens, they're probably not going to believe you as much as if you say I was just too lazy. Again, that doesn't mean they're going to excuse you. That's a whole different question. But like believing is the first part of this. They're more likely to believe you are too lazy and then maybe your dog ate your homework, and then in a very rare universe that you were abducted by aliens. So that tells us about this question of when I said prior probabilities in the pizza example might have been like, I know this pizza place is better than this one, or in my view this pizza place is better than this one. So that has to do with what you have heard from your friends about this pizza place. It does not mean you've seen the data, but it just means that you have some knowledge about this. And so, yeah, according to Bayes' rule, if you remember, prior equal to likelihood times, oh, sorry. This is called posterior. Likelihood times prior divided by a normalizing constant. Normalizing constant has nothing to do with the normal distribution. It's just a fixed term that makes this sum up to 1. That was the point. Well, not yeah. makes it a distribution from a density. Yeah, that's what a normalizing constant is. Difference between distribution and density. Density is unnormalized, distribution is normalized. We have probability distribution because all of those sum to 1. Probability densities do not necessarily sum to 1. So densities can have very high values. But when you normalize it, the density reduces to where the area under the curve is 1. So remember the difference between distribution and density, please. So, okay, I'll do this slide and then I'll give you a break for 5 minutes. So what in maximum a posteriori estimation, as we've already discussed, but now more formally, you want to find this posterior distribution of the weights given your data. So you want to, the weights were, remember, the ingredients, quantities, or in this case also ranges, or updated ranges to be more precise. So, well, I guess this entire thing is updated ranges. This is just the ingredient quantities, and this entire thing indicates, like, after I see my data, what are the updated set of ingredients? And there, the Bayes rule tells us that this is proportional. Oh wow, I've been really just tapping all over the place. Sorry for that. Bayes rule tells us this is proportional to the data likelihood. Now remember, this is the likelihood that we've been discussing all this while. The probability of x given the weights. So x given mu and sigma is the likelihood, the data likelihood under the model, times the prior probability of that model. The belief I have that this pizza place is the right one, times the probability of this mozzarella basil pie at this pizza place. Multiplying these two will be proportional to finding this updated probability of whether this mozzarella basil pie is possible to make at this certain place, or how likely that is. And then you take the negative logs of all of these. So let me clear this out, or pause for a second. This is clear to everyone, how we went from Bayes rule in the example to this posterior probability to figuring out like how this is related to the likelihood and prior. Okay, I'll if there are questions, feel free to post in chat and I'll continue. I can clear that out. So we went to these terms because calculation is easier. And then we went to this minimizing of the log. We don't care about the constant terms because they won't be affected by this anyway. So they are a certain fixed value, which are not affected by the minimization. So minimizing this entire thing is the same as minimizing this thing, which is these two terms. That's all they're saying. And in the homework example, so that is this is our goal, our optimization problem. And what we start with is what he's saying, that this log prior, the prior that you place over all of these explanations for why you didn't do your homework. It seems like I've lost my internet on my laptop again, so I'm going to try and reconnect. Let me stop the recording and give you the break at this point. I will be back in 5 to 7 minutes. Cool. So we said you have to place some priors over your explanations for the reason your homework was not done, right? And the prior that your TA might have is, okay, I believe that you're a lazy student. I may or may not believe sickness in family. It's very, very unlikely that your dog ate it. And it's even more unlikely that an alien would abduct you and then return you and then let you submit your homework. So those are my priors. The data might support something different. That is why we update these priors into posteriors. And these posteriors then dictate what we believe. So you can think about it as a posterior being a distribution, but there can be a mean for that distribution that you can just take as this maximum. So the maximum a posteriori estimate is just placing a mean or over that distribution, taking the mean. And this might make or help you think about this question that, well, but in what cases is that mean the same as the point estimate for my maximum likelihood? Remember this point estimate? Well, if you're saying that I update my priors into a posterior distribution, what if the distribution is the same as the maximum likelihood estimate, and then that distribution, the mean of that distribution is at the same point as this final optimal point you get from the maximum likelihood estimate? Yes, that is true, and that is often the case with certain situations in which you place uniform priors. So uniform prior basically means I think everything is equally likely. So I can't give anything more value. So I just distribute all of my probability over my parameter space uniformly. So in a sense, a uniform prior is also an uninformative prior, because you're not saying anything is more likely than something else. A uniform prior in this case would be just give all four explanations a probability of 0.25, right? You're not saying anything is more or less likely than the other. And in that case, when you update it, you would arrive at the same solution as the maximum likelihood estimate would tell you. So you're not, and there is no intuition involved here, which is why it reduces to the same case. And that is possible and that is fair. But if you're using this approach, then typically you want to use some of the extra information you might have beforehand, some of your knowledge, your experience, your intuition. And that helps you improve upon your maximum likelihood estimate. So that's the key idea here. But the next question is, what does this have to do with regression? Well, if you remember, the regression, the optimization problem we had, which was we used the mean squared error, right? The error tells us if this model works or not. We used some additive Gaussian noise, which we called white noise. And I'm sorry if my screen has this video on it. I should move it aside. There we go. Yes, okay. Cool. So if you recall our optimization problem, there was a part that had the error term. The model had a additive Gaussian noise because we said the data generation model for this was y is equal to f of x and w plus epsilon, where epsilon was this what we called white noise. And because we don't know anything about this noise, we said it was drawn from a normal distribution, which was zero mean and had some sort of sigma squared variance. And we said this f of xw just shifts this noise distribution by x transpose w plus b or whatever. Then we said b was included in w because we added one column of ones there. We said this x, we add one column of ones. So this is a certain fixed value. Anyway, going back to the prior distribution placed over the weights, if we do that, then this reduces to a problem where your log prior probability is equal to the same. Where did we go? I feel like I lost a slide. Yep, I think I did. Don't know what I did, but seem to have lost that slide. Well, I was just going for the P of X slide, but you already know P of X, so maybe I don't have to go back. It's really weird. Yeah. Anyway, I was going for the functional form of the normal distribution. The way we got this, this last term, the prior and the log prior, and if this is a normal prior, then this will be the form of the likelihood for this. This will be the form of the prior of the log prior. Anyway, the maximum a posteriori estimate then is again minimizing this log likelihood, minimizing this negative log likelihood. So NLL is this term you will come across a lot. And we already discussed why we take negative, why we take the minimization instead of maximization, why we take the log instead of the just the prior distribution. And so this is the maximizing the posterior, minimizing the negative log likelihood equivalently. So this reduces to a certain minimization problem. I think the first line is fairly straightforward. This is just the same expansion. Now you have a certain error term and you have a certain regularization term. This lambda is equal to this, just when you multiply this entire thing by sigma square, which is a constant. Okay, let me annotate this. My iPad is back, so I should be able to. So I am recording, right? Yes, cool. So we first get the, what do I want to say? This is the, sorry, realize I've not been writing. So this is fairly straightforward. The way we get from here to here is you multiply this entire thing by sigma square, and then you divide that by n. I think that's what you do, right? Yeah, sigma squared by n. I believe this is the case, so that the sigma square goes away, and then there is an n term, and this is switching this finger of mine. This becomes sigma square by sigma bar square n, which you then rewrite as lambda. And so this results in the form of the equation that you get when you generally talk about this regularization term plus minimizing this loss function, which is the same as, now we started with maximum a posteriori estimation. And that's all I want to say about that. It's interesting. It's that a lot of different ways of framing the problem result in the same optimization procedure. And there are a number of ways to solve this optimization procedure. You've seen gradient descent, but there are other ways. Like at the end of the day, it's just this, right? This. I mean, oh, I can't clear the other terms. Are you serious? Can I clear everything? Clear all drawings. Great. Okay. Excellent. So ultimately, it's just a question of this, and this can be solved in a variety of different ways. And by a number of different ways, I'm talking about numerical methods now. There are Newton, quasi-Newton methods, Newton-Raphson method, second derivative based approaches, taking the gradient of the gradient to figure out how fast your learning rate should adapt and stuff like that. But anyway, you know gradient descent. That is one of the popular ways, and we can move forward with that. One of the discussions that came up, there is a chat. Regularization is just a way of enforcing some constraints on the model parameters. You're absolutely right. One of the main discussions we had, I think a while back, someone asked about this, is what sorts of loss functions do we use and why? So all of this discussion was about squared loss, but not really. We haven't talked about loss. Yeah, I guess this has to do with that. Yeah. Anyway, coming back to the point was there are different loss functions, and at some point someone was asking about, well, what if we use mean absolute error, and what if we use a I mentioned that there was a combination of both of those terms called the elastic net, if I'm not mistaken. But point being, you can measure losses in different ways. For you, the best pizza might be something that tastes really similar. For someone else, it might be something that's hot and tastes similar. For a third person, it might just be that it looks similar. So that this metric of best depends very highly on like what error function you use. So taste might be one, looks might be another. There might be a combination of taste and looks. There might be price that plays in, who knows. And so everything is subjective depending on your choice of error function. And you would hope that your error is based on the problem that you're solving. So there are specific errors that are relevant to specific problems you're solving, in some cases, which is just to say like some errors are better than other errors under some constraint of the problems you're solving. I don't have a great example for you off the top of my head, so I won't confuse you. But like the bottom line was the choice of error is subjective, and you can choose the error function of your choice for a problem you're solving. In blue, you have in blue you have this loss function, and as you can see, it's a squared term. So this is a parabola. In green, you have certain normalized likelihood using this function. And in yellow, you have the gradient of normalized likelihood. So you can see that this gradient is roughly 0 at the mean. So if you use gradient based optimization and this is your likelihood, you're basically going to end up at this point, saying that this is your minima of the negative log likelihood, and equivalently where the loss is the least. Cool. So this is just representing that it's going to push you in that direction. The red lines indicate where the gradients are going. So here the gradients are negative, so you want to go upwards. Here the gradients are positive, so you want to go downwards. That's all this is saying. Okay, let's clear this out. And this was the squared loss, right? The L2 loss, the Frobenius. Well, it's not a loss, but yeah, no. The L1 loss was the mean absolute error, which is saying mod y minus y prime, which is your target minus your prediction, or your target minus your guesses, whatever you want to call it. Again, in blue, we have the loss. Oh, oops. Blue, we have the loss. Green. If you happen to know what distribution this is, I don't think it has a name, this distribution. Yeah, I don't. Yeah, sorry. I guess I don't happen to know. I've never seen this named. It's just called the if I don't know what it's called. It's just like there's a kink at the origin and there are two slope lines equal in either direction. But yeah, I'm sorry about not having terminology tied down there. So in blue we have the loss function. In green we have the normalized likelihood. And in yellow we have the gradient. And now this is interesting, right? So the gradient is either always 1 or always -1, depending on which side of the origin you are at. And at the origin, this is problematic because it is not clearly defined whether it is 1 or -1. So that's what people say when they say that, with this loss function, you have a problem with gradients because at the origin, the gradient is not defined. So unless you define it as a specific value at the origin, this is not continuously differentiable. So yeah, I guess that's all I want to say about that loss function and geometrically what it means. This is just indicating where the gradients push you when you're on either side of this loss function, right? So it is pushing you to the minima, but at the minima, you won't know what the value is. Because this, again, at 0, this gradient is not clearly defined. Cool. And then someone, or I guess Huber, came up with this idea of robust loss. William Huber? I don't know the full name. But anyway, he defined this loss function as between 1 and -1. He said this is the squared loss. No, wait. Yeah. Yeah, between 1 and -1, he said this was the squared loss. And outside of 1 and -1, he said this was the L1 loss, or L2 loss and then L1 loss. And I guess that's what I want to say about this. It's just one way of combining multiple loss functions. And you can do this. You can actually implement such sorts of losses in practice. So in practice, people have come up with triplet losses. So you take 3 points, you maximize the distance from the points that are not in the same class, and you minimize the distance to the points that are in the same class. So those are, I think, called triplet losses, or I think contrastive losses fall into this class of triplet losses, or vice versa. But the idea is you contrast data points with something in their own class, which you want to bring it close to, and something in different classes, which you want to push it further from. And so that's not necessarily one following one certain like L2 or L1. It's a combination of all of these different kinds of losses. So yeah, that's what I want to say about that. Robust loss, I think Smola made some points about outliers and how it handles outliers. I don't, you should watch the video to go through that, but I don't think it's super relevant to mention. I guess the point he was trying to drive home is different kinds of losses exist for different problems. Every problem will not work with the same loss function, which is again what we started out with, that loss functions might be very problem specific. And in fact, a lot of machine learning papers are based around the fact that, look, we came up with a new loss function for this problem and it works really well for a bunch of such examples. Ultimately, what your loss function is doing is getting you closer to a set of parameters that predict well. So all of this is designed to get you that optimal set of parameters. And the more optimal or optimality is defined in terms of a loss. So the better or more, oh, there are chats. The better your loss functions, the clearer, no, there are no chats. Okay. The better your loss function is for the problem, the better you're going to get to an optimal solution that that helps you predict really well on future data. So yeah, so you're right that robustness implies it isn't influenced by outliers, and that's the discussion he has in the video. I didn't bring that up because right now I felt like it's not super important to mention that. But anyway, that is, I think that's all I'm going to say. Moving on to yeah, this is fine. Moving on to logistic regression. I have about 10-15 minutes to cover this, so it should be enough. So we have discussed regression as taking a set of x's to predict a set of y's. Right now, we didn't say what this y was. The assumption it was a real valued function. So you take some x's multiplied by a w and predict a certain y. But now in classification problems, we have certain sets, like a fixed number of y's, right? There are certain categories. So it's not that y is real valued, but it's that y falls into a number of classes, or y defines y as a set of classes. And one popular example is 10 classes, 10 digits, 0 to 9, right? So you want to given a set of inputs as image format, pixel values, you want to predict which digit is this. And so there is a fixed set of y's, and it reduces to a classification problem. And why do I say reduces to? The implication is you're still solving a regression problem, but you are casting it into a certain different output. And this is true, like this is how it works. Essentially, all we're doing is regression, but now we are putting something on top of that regression to convert that real valued y into these classes. And so what is that? Before that, though, that like I said, there's other examples. Like there are 1,000 classes in the ImageNet data set, which is just this representative real world data set. When I say representative, it means like if in theory, if a model does well on ImageNet, it should do well in the world because there are so many classes of things in ImageNet that it is well representative of the world. Going back to a good sample of the world, the discussion we had about if this food is a great sample of the restaurant food quality. So that way, so someone sat and created a data set with a lot of effort. I think Feifei Li's group at Stanford went and created this ImageNet challenge, and it's been the de facto standard for a long time. And there have been augmentations to that data set, but that's been like the go-to place to see, look, our model does really well on ImageNet. That is a big deal. Okay. Moving on, other examples of this are classifying a human protein image into different categories, classifying malware into different categories, classifying toxic Wikipedia comments into different levels of toxicity. And so, like I said, when I say reduce a regression to a classification problem, you want to go from this real valued output to a fixed class output. And so based on these real valued, like it's like saying I want to go from grading students on 0 to 100 to pass fail, right? Now sure, someone who got 55 probably passed because if your pass bar is set to half. I should have asked you that other question, but in the interest of time, I answered that. The question is, how would you go from a 0 to 100 score to a pass fail? And the obvious answer, or at least I think it's obvious, is you set a threshold, right? Above 35%, if you score above 35%, you pass, otherwise you fail. And it's the same way with regression, like you set a threshold, and then above that, it belongs to a certain class, below that, it doesn't. But now the challenge is you're wasting some information, right? So you are saying something that falls 1 point above passing marks is equal to something that falls 30, 40 points above passing mark. And so you want to use that information somehow, and you want these scores to indicate the confidence that it belongs to a certain class. And so you treat these as probabilities. And so like you want to cast this 0 to 100 as a percentage or whatever, not as a percentage, as a probability of your confidence that the student is passing, which in this case could be the percentage. Yeah, Deep raises an important point. Such a big ImageNet data set is still considered to be biased and imperfect. Like there are multiple additional versions of ImageNet where, and we can discuss this separately, like at length in convolutional neural networks, but ImageNet's still missing some things like the like we will discuss later. But ImageNet is not perfect. So cool. So you want your scores to reflect some sort of confidence. We've already discussed what's on the left, right? Let me redo this. So I have my cursor. Yeah, on the left, we have we have a natural scale in R, y belongs to R. We have a single continuous output. We have a certain loss given in terms of y minus fx. We've already discussed this. What we want is that there might be multiple classes, so multiple outputs. the score should reflect some sort of confidence. So we don't just want a yes or no answer. We want a yes with certain probability answer. And so we might think of one hot encoding each class. So you expand the y's. You say that now there are 10 values of y, and I place a 1 wherever it's a true class, and I place a 0 everywhere else. That's called one hot encoding. So if I have just the y label, so if in my original problem, if I just had the digits 0, 1, 2, 3, 4, now I expand this to an array, and at 0, I put 1. In the second array, at the label 1, I put a 1. So indicating that this is the correct label and the others are all zeros. Hopefully this was clear, but it's called one hot encoding. So wherever this array is hot or it has the 1, it indicates that this is the correct label and everything else is not. And the reason we do this is because it gives us this when you have outputs, you can just take the max of this array, like argmax or index of max, and you say that is the predicted class. So y might still be real valued, right? The output for y is still real valued, but the target is this one hot vector. So if you want to find the closest prediction is just the one that is closest to 1. I should probably write this down to make it easier. Y target, or I should just write y is equal to, I'm taking 3 classes here, and the y hat or y predicted is equal to 0.33, 0.46, 0.98. And the argmax, can someone tell me the argmax of y hat? Shivranil says 0.98. You are correct, but you told me the max of y hat. What is the max of y hat? This would be 0.98. The argmax is the argument that maximizes y hat. So y hat of what will be maximum? This is the question I'm asking. So the question mark is equal to 2. Well, it's 0 indexed array. I forgot to say that. So this is index 0, this is index 1, this is index 2. Right? So y hat of 2 is equal to equal to max of y. So 2 is equal to arg max of y hat. Sorry, should have said y hat. Sorry, I confused you. But yeah, hopefully this is clear. So yeah, just the difference between argmax and max. It took me a while to get that the first time, so don't blame yourself if you missed that. But it's just the argument that maximizes versus the actual maxima. And the reason I'm taking the argument is because it tells me the class. So this is class 0, class 1, class 2. Then I predict that the prediction is actually class 2, which is wrong, right? Because this is actually class 1. That is the true label. So this is how one hot encoding will work with your argmax and your score, and the largest output would win. So that's how you train these classifiers. Moving on. I see I don't see any questions in the chat. So yeah, it's a question of, we want that the correct class is recognized confidently, right? So you want that your true output minus your predicted output, so OY minus OI, is greater than or equal to some delta, some difference between Y and I. And the way this is realized is by taking, again, the negative log likelihood. So there is a certain function that squashes, or how do I want to explain this? The way your real valued y is squashed into a probability, because again, there is no, right now, we just predict some y. There is no necessity that this has to be 0.1 point, sorry, what did I say, 0.33. This could have been 6.33. Y hat could just as well have been 6.33, 4.98, and 7.98. And so in order to predict probabilities, in order to ensure that these are probabilities, we use some f of y hat, which is called the softmax, and exponentiated sigmoid, yes, whatever you like. There are different squashing functions, and just like there are different loss functions. So essentially, it's a function that maps r into 0, 1. This is how you mathematically write it, a function that maps a real valued output into a space that is just 0 and 1. That's why it's called squashing. And one of those functions that has a nice gradient to work with is the softmax. And so we use this softmax function to squash this and normalize our outputs into probability values. So now we can say that, okay, using the softmax, now I'm sure that my y, the output of my predictions will be a probability. So now you have a set of probabilities as your output, and then you can work with that. That's all I wanted to say. There is a certain loss called cross entropy loss. I will actually hold off on cross entropy. And we can discuss that in the office hours because we're running out of time here. What do I want to say about cross entropy? I don't feel like I have anything special to say. I will. Do the TAs have any thoughts? Yeah, okay, we'll be going through cross entropy tomorrow during the recitation. Yeah, fair enough. That's great. In that case, I will pause here. I will stop here and take your questions for whatever this regression stuff that I covered rather quickly, going from regression to classification and then dumping this softmax or popping the softmax on top to convert this to class probabilities, and then going from these class probabilities to class predictions using this argmax. It's fairly straightforward stuff. It's just that people combine all of this and name it different things, and they don't sit and very easily explain it. So blog posts are found are really nice to read about all of these things because they're fairly simple. But yeah, this is where I will pause. I really want to get into a bit of information theory. Maybe 1 or 2 more minutes. I'm sorry about this. Suppose you have some data source that produces some observations, and you want to quantify how much information is in this source, right? For instance, if you compare like coin tosses and dice rolling, which one has more information? How do you quantify that? Well, it's super hard. Like you and I can't decide that 3 coin tosses has more information than 2 dice rolls. And so it's complicated, but the way some people did this is you measure the number of bits needed to encode that information. And then suddenly you have a uniform metric to evaluate the information contained in all different kinds of data. Right? So this measure is the minimum number of bits needed to encode this information. And this we call entropy, or as entropy is defined. Oh, I should clear my screen. I'm really sorry about that. As entropy is defined, it is the lower bound on the number of bits that is required to encode some data. And I won't spend a lot of time on this, the notation. That's fine. You can read that yourself. But think about it as an entropy is a concave term since P log P is convex, right? So yeah, I don't want to say anything about that. It's entropy is defined as minus Pj times log Pj for all j in your data. Yeah, I don't want to say more about that, but I want to stop it after examples. So for a fair coin, so okay, so in a hand, let's think about this. Is if I tell you a coin is fair versus a coin is biased towards heads, like Amitabh Bachchan's coin in Sholay, which constantly flipped heads, which one would have more entropy? I don't know if that's too hard a question to start off with. So we one answer the fair coin, one answer the biased one, another answer the fair one, the fair one. Okay, so let me give you some more information and then ask you again. Suppose I tell you I know nothing about the world, like everything is equally likely. And suppose I tell you, or let's go back to the example we had. Suppose I tell you that I have no idea, I'm not a chef, and I can't tell you which pizzas are better to start off with as candidates to get to this ideal point, right? And suppose in another case, or case B, let's say. So case A was I'm not a chef, I don't know which pizza to start with. Case B, I am a chef, I know that margaritas will get you closer to mozzarella basil pies. In which case, A or B, am I giving you more information? Okay, it seems more clear now that, okay, in case B, I am a chef, so I know some things and I'm giving you more information about where to start. So more information results in less entropy, because entropy in a sense is chaos. How much chaos is there and how much uncertainty is there in the world. The less the information you have, the more chaos there is because the more uncertain you are about the world, right? So now going back to the point about fair coins and biased coins, if I'm telling you that it's a fair coin, then in a sense I'm also telling you nothing about which what will it flip. But if I'm telling you it's a biased coin, I'm telling you that, oh, it's more likely to flip tails than heads. So now you have more information about predicting that this will have tails more often than heads. And therefore the information entropy for a fair coin is more, the uncertainty is more for a fair coin, which is this 1 bit, as compared to an unfair coin where I'm fairly certain that this is going to flip tails more often. And so I just wanted to give you this informal intuition, and you can read about the formalism and come back to me with questions for the officers. Like I said, there'll be 2 or 3 this week. But that's what people talk about when they say entropy and uncertainty, and you want to. I haven't gotten to divergences yet, but when you want to compare 2 distributions, but you don't. No, never mind. Too complicated. Yeah, I guess so. Naturally, a 20-sided dice will have a lot more entropy than a 2-sided dice, than a 2-sided coin. So now you can think about okay, now we have a measure, a uniform measure to compare very different items in terms of uncertainty and certainty purely. So that's all I wanted to motivate. This is the idea of entropy. And also tie it back to our case of priors and prior problem and posteriors. Okay, I will stop here, or I will stop here and take questions if you have any. You can unmute yourself if you like. Oh, what does this have to do with regression? This doesn't have as much to do with regression as it does with deriving some of the items you will need moving forward. So in a lot of, like I said, I haven't given you all of the tools, like gone from entropy to divergences, but it's in the readings, like how do you compare distributions? How do you claim two distributions are similar or different? How do you compare different values, experiments and outcomes in this uniform metric, using this metric of information entropy? It features a lot in different places where you have log PDFs, because you might think of, if you define something in terms of, I should clear the screen. If you define something in terms of this notation, you realize that, oh, I've seen this notation before, or if you haven't, then you will be seeing a lot of this, p log q, p log p, whatever. Yeah, but so far not a lot. In the future, a lot. Okay, a bit of a subjective question. Do you think if you model some classification problem with a softmax function, do you think the probabilities that pop out are valuable for a simulation-based project? Depends on the framing of your problem. Like, what do you want the outputs to represent? And if your simulation, if by simulation you just mean you want your model to generate more data, then sure, like more realistic values will always help you simulate better data. But there are a number of ways to do that. It's not, this is a reasonable approach, but like there are other ways to improve your simulation. There are different divergences that you should consider, because at the end of the day, you are comparing two data generating processes. One is the true one of the world, and one is the model you have that you think represents the world. Your goal is to make this model more similar to this true process, which can be done by a number of ways, one of which might be regression. Um, Others might be slightly more complex, and you might want to use neural networks, just because it can approximate the data a bit better, assuming that you have enough data to work with. Sure, sounds good. I'm a little unclear between cross entropy and KL divergence, specifically the symmetricity. This is a great question, and the reason I didn't want to get into KL divergence is because I didn't actually give you the tools to understand all of that. Like I said, I wanted to, but the timings were off. But I can take this up in the office hours in detail, given that like I will tell more people. So I have my office hours on Tuesday night, India time, I believe. And by then, more people will have had time to read this. So I can give you a separate mini tutorial on what is a divergence, why do we care about divergences, where did the KL divergence come from, what is the cross entropy. But right now, to answer your question, it compares two different objects. So while divergence is compare distributions, cross entropy compares samples, if that helps. And if I can make it even more precise, divergence, to my understanding, KL divergence compares if this normal distribution and this normal distribution is similar, versus cross entropy compares this normal sample and this normal sample. We shouldn't have this. It tells you if these two samples are similar. In a sense, 5 pizzas to the whole menu. Exactly. So to be very even more precise, the distribution is, I guess, yeah, you can say the whole menu, like an infinite set of items in the ingredient space, right? Because if you're using samples to approximate this to like define this distribution, then you need infinite samples, right? Like infinite points along a line. So if you're saying infinite item menu, yes. Because we defined the ingredient space as continuous. If we had defined it as discrete, then there would be a finite set of items. But yeah, like there can be 1 gram, 2 gram, 3 gram, 1.5 gram of salt or whatever. So that's the reason I said, like, sure, whole menu, but like a whole infinite menu. Like every single item possible to make at that restaurant, whether it is food or not food, just in the sense that it is made with some ingredients. If you're comparing that across 2 restaurants versus if you're taking like 5 items and comparing.
If I'm the same person who asked that doubt, if we were to extrapolate this knowledge to say events and probability, how would you say that? Like entropy would technically be like the uncertainty of the events and the likelihood that one event could cause the other, right? Or am I wrong?
I didn't gather your last point. Uncertainty would be the likelihood of one event. Sorry, could you repeat?
Yeah, sorry. I said the cross entropy would be the uncertainty that one event caused the other, right? Like in terms of probability and events, I'm trying to understand it.
Is close to. Caused is, I'm not even getting into causation. We're talking currently about distances and divergences, like the difference between two values. Are you still there?
Yeah, I think I got a little confused. Yeah.
Yeah, I'm just talking about so think about this, the difference between 2 points in Euclidean space, your x and y axis. Now take like multiple samples. So you take the difference between 5 points in Euclidean space. And now take a whole distribution in x along the x and y axis in 2D and compare those two things. So you're moving one step up in the same space, but like you need different metrics to evaluate them. You can't use the same metrics.
Right. So basically like the whole data set versus a mini batch of sorts, kind of.
Yeah, in a sense, except the whole data set is infinite, right? Like we said,
right.
If you can't define a plane in terms of points.
Mm-hmm.
That's why you use equations for a plane. You don't say like x1, y1, x2, y2. Whereas in terms of points, you actually do define them as x1, y1, and x2, y2.
Right, got it.
So that's, yeah.
Thanks.
Sure. And yeah, one very important point to mention is when you're talking about distributions, especially with the KL divergence, KLQP, or like the difference between Q and P, is not the same as KLPQ, which is very counterintuitive because all the distances that we've learned about in undergrad were like, oh, distance between X and Y is the same as distance between Y and X, just reverse the signs and you're good. So yeah, there are certain nuances that you have to deal with, and the KL is an asymmetric distance. So that's also why I didn't want to get into that without allowing you a chance to read a bit more about that. Maybe also watch his information theory video. And I've gone a lot over time, so I'm going to stop recording here.